So I'd like to welcome everyone. My name is Jean Creighton, and I'm here in my capacity as a member of the Great Lakes Planetarium Association and a member of the International Planetarium Society. And it is my very great pleasure to introduce Michelle Thaller, who I met in California when we were both working at IPAC. And at that point, this is now 25 years ago almost, I was thinking of moving from Pasadena, beautiful Pasadena, to Milwaukee. And everybody in California was saying, you know, I might as well have been going to Angola the way they were talking about it. And it was Michelle, the first person who said to me, no, this is a great place. You'll love it. And I still have the list that you gave me of the places that you need to check out when you're here. So Michelle Thaller has always been a wonderful, friendly person in my books. So I'm very glad that she's here to talk to us about the power of the sun and how it affects us on Earth. So Michelle, take it away.
Okay. Hey, well, thank you so much, Jean. Really nice to see you again. And the reason I was recommending Milwaukee is that's where I'm from. And yeah, the winters are kind of long, but other than that, it's a beautiful place to live. Pasadena, I have to say, has to be one of the nicest places to live in the country. But I would put Milwaukee pretty close to that. I love living in Milwaukee. Maybe I'll get back there. Right now, I work at NASA's Goddard Space Flight Center, where I'm one of the sort of under directors of science. And, you know, I have a chance to really talk about pretty much all of the science that NASA does. And happy Earth Day, everybody. You know, we're doing a big campaign both for Earth Day and the next Crew 2 launch that's going up on the SpaceX rocket, hopefully tomorrow. Or has it gone to Saturday now? I forget. But so we're doing a lot of coverage of that. And I think it's kind of a fun day. You know, Jean asked me to talk about things relating to the sun. And, you know, I sort of have prepared a presentation about the wide ranging effects of the sun on the solar system, and indeed, even like the habitability of planets. And of course, everything that I'm going to show you is available on NASA websites, free for your use. If anybody wants the slides afterwards and the animations, I'd certainly be happy to provide them. And I'll try to stop a little bit before 3 o'clock so we have a chance to answer some questions. But anyway, I'm actually a stellar astrophysicist. That was my doctorate. It was in the structures of stars. I specialize in stars that are a little bit more massive than the sun, but I actually do specialize in stellar winds. And so you'll see that one of the things I'm going to talk to you today about is what is the solar wind and what does it do? So let's see, you know, in broader context, more about the sun. So let me share my screen. I have some slides prepared for you. And okay, here we go. So let me just put this on. All right. Okay, you know, I actually have the really nice gig of having a little side job for the Smithsonian, where they will bring me along if they need an astronomer or a space physicist to give talks. And oops, come back here. And I actually do trips to Iceland. I did not take this picture, but you know, one of the things, of course, you're probably aware of is that the solar wind is responsible for particles coming into our atmosphere and actually sort of exciting the gases in our atmosphere to glow. It's you know, one of the ways we most directly see the solar wind. So we're going to talk about the sun's effects, and just to kind of, again, I know I'm dealing to people here who know a lot about this, but you know, there's a picture of our star, and there's the Earth in scale. It's always worth, you know, reminding the public. It still is mind blowing that you could fit more than 1 million Earths inside the sun. It's that large, and you know, it's sort of wonderful to do these comparisons. So when I show you pictures of solar prominences and space weather and that, you can sort of calibrate with how big those things are compared to the Earth. So the sun, very simply, as you know, is a big ball of hydrogen gas, mainly hydrogen, you know, about 20% helium, a smattering of everything else that was in the cloud that formed the sun and the Earth about 5 billion years ago. And in some ways, it's very simple. It's just a big collection of, like I said, mainly hydrogen. Gravity crushed it together inside a cloud that was forming stars. And that's, of course, how our whole solar system formed. And eventually, you know, all of that crush of gravity began to raise the temperature inside higher and higher and higher. And when you raise the temperature of a lot of hydrogen up until a couple tens of millions of degrees, then you will get nuclear fusion. And this nuclear fusion reaction creates heat and high energy radiation, all kinds of wonderful stuff in the very core of the sun. And the core is the only place, by the way, that these reactions happen. at least during any kind of normal part of the sun's life. When the sun begins to die, some of the nuclear reactions may move a little bit farther out, but the core is really the only place that you get nuclear reactions. And everything on top is just gas being heated by that nuclear reaction in the middle. So we're going to be talking about some different parts of the sun. So in the middle, you see the core. That's where the nuclear action is going on. And then there's a radiative zone, which basically means that everything is so hot in there that radiation almost sort of freely moves outward. It's very, very dense, but radiation it's not really changing the structure of the gas around it. It's just becoming very hot. And then above that, there's actually a region here, it's called the convective zone, and we'll take a look at that. And this is where some of the heat from the sun gets trapped and begins to create convection cells, almost like clouds on a hot day. Warm material rising, then cooling, and then sinking again. That's convection. So convection is basically the cycle where something is very hot. Therefore, on Earth, we see it rises into our atmosphere. In the case of the sun, it rises, away from the core. And then when it cools down, it sinks back again. So there's this cycle, this convection going on. And then the other things we'll be talking about is the surface of the sun. You'll notice at the very bottom, there's a little label that says granulation on surface. That's basically the tops of all these convection clouds. And we're going to talk about that. But the really important thing we're going to talk about today is something called the corona. And the corona, you'll see that the little arrow goes not to the sun's surface, but to a little bit above it. And this is the outer atmosphere of the sun. And in some ways, you can say that the outer atmosphere of the sun almost defines our entire solar system. It will have effects, the corona and also the solar wind of particles that comes out of it. This will have effects all the way out to beyond the orbits of Pluto. So it's amazing to think that we actually live in this wonderful environment created by the sun. It's not something we're aware of very much. Now, this is a little video I'm going to play that's going to go through some of the layers of the sun that you just saw. And it's also going to be a little coming attraction to a few of the topics we're going to talk about today. So let me play my little video and I'll turn it up so you guys can hear it.
The sun's core is the hottest part of the sun, but our star's temperature doesn't behave as you might expect. The core is roughly 27 million degrees Fahrenheit and 10 times more dense than gold. As you move outward, the layers of the sun become cooler and less dense. Something unusual, however, occurs when you reach the outermost layer. While the surface is around 10,000 degrees Fahrenheit, the corona, the sun's outer atmosphere, is several hundred times hotter. That's the opposite of what happens with a fire. When it gets cooler, the farther away you get. Scientists call this the coronal heating problem. It remains one of the greatest unanswered questions in astrophysics. The corona extends for millions of miles and continues outward as the solar wind, which bathes Earth and the entire solar system. This tenuous region consists of superhot elements such as hydrogen, helium, and iron. There are a variety of theories for what mechanisms could be adding that extra heat into the atmosphere. Scientists think it may be the result of the sun's convective motion that acts like boiling water and tangles magnetic fields on the surface. One theory suggests these tangled fields create small waves that push particles and heat from the surface into the atmosphere, like how ocean waves push surface. Another theory suggests small bomb-like explosions from the realignment of the sun's magnetic field create heat. Many scientists think it may be a mix of both. We've studied the corona from Earth and satellites, but to solve our star's biggest mystery, we have to make direct observations from the region itself.
Indeed, that's what we're going to talk about today, is doing observations of every part of the sun that we can see. Obviously, we can't see any farther below the surface, but we can see what's going on the surface and right above the surface, and also the extent of this particle wind. And it may surprise you. So people, we talk about wind, and that's something that members of the public have a very distinct idea. They're thinking of the wind in our atmosphere. And in the case of the sun, of course, it's very different. It's not, waves of density in something like a dense atmosphere, but it's a wind of particles themselves. And as they mentioned, you have hydrogen, you have helium, sometimes you have other species like iron that you can actually find from the solar wind. And the temperature is many millions of degrees. And this was a really big mystery as far as how the sun worked. That how can you have the surface be 10,000 degrees, but right above the gas is in the millions of degrees? It also may surprise you to learn that we are right now being bathed in million-degree gas, and that's actually true. And I think that, one of the big obvious questions you get from the public is, how come we're all not burned to a crisp then, if we're living in this 1,000,000-degree gas? And that's it's a rather complex idea about how we really feel temperature. That, we really only feel temperature when there's enough stuff, when it's dense enough for things to conduct heat to us. We're not used to just particle by particle hitting us and getting our temperature that way. One of the best real life examples I can think of this, and of course you have to do all kinds of do not hurt yourself, is if you set your oven to 500 degrees, that if you were to touch like one of the metal trays inside there, or touch a pot in that, you would burn your hand, right? It's at 500 degrees. But if you just open the oven and stick your hand in and just feel the air in there, it doesn't burn you. I mean, you can tell it's warm, but it doesn't actually burn your hand, because the air is not actually dense enough to actually really conduct that much heat to you. And so, the same thing in our atmosphere. We are surrounded by, oh, here goes one proton, zoom, here goes one helium nucleus, boom. I mean, they're going so fast that they have the equivalent temperature of many millions of degrees, but they're also very thin. And because of that, they don't heat us to a temperature of many millions of degrees. Okay, so studying the sun, we have a number of amazing new tools we're going to talk about today. We're going to talk about those effects that they mentioned in this video, but also we're going to talk about how we observe them. And just in the last couple of years, we have had some absolutely incredible new tools for observing the sun. And this is a picture of a telescope that came online, I believe in 2018, called the Daniel K. Inouye telescope. Daniel Inouye was a senator from the state of Hawaii. And this telescope was built on Maui. It's on the big island of Maui, up on the Haleakala Peak. And here's I love these wonderful real scale pictures of these telescopes. They're absolutely huge. I love visiting these. And this giant telescope is able to produce the highest resolution images of the sun we've ever taken. And these things are absolutely incredible. I'll tell you a little bit about it, but I want you to pay attention. Look at all these little wires. The primary mirror, the big mirror, is in here. And there's all these little wires and loops on the outside. I just want to mention those because I'm a fan of this. But that's how big this particular solar telescope is. And it's able to take images like this. All right, now we mentioned that the top of the sun is convective. There are hot, big pockets of gas that are coming up from the warmer subsurface, cooling off, and then coming back down. And it's kind of strange to think of. I mean, there's no real like solid surface to the sun. I mean, the density of the outer layers of the sun is really not much more than the density of air here on Earth. So you're not talking about blobs like of lava. You're talking about gas, fairly thin gas. And but the gas, I mean, just like in our atmosphere, forming clouds, it can go up, it can warm up, then cool down. So you're looking here at basically the top. I mean, people often compare this to like a pot of boiling oatmeal. There's all these bubbling things all over, and you're looking down on that here as we look at the surface of the sun. But to give you an idea of the scale of this, this was one of the graphics I found from the National Science Foundation. That is one of the groups that runs the DKIS telescope. You're looking at these huge convective cells. And they've highlighted one in the upper right-hand side that's about the size of the state of Texas. That's how big these things are. And then the very smallest structures we can see, and we had never been able to see these structures before, are things about, say, the size of Manhattan. So you can see there's a tiny little dot there that's actually real data. And that's about the size of Manhattan. So, these cells can get bigger than Texas, or they can be kind of small and sort of city-sized. That's about the limit of this particular telescope's resolution. There's probably more structure that's even smaller. As most of you probably know, the reason we want to build bigger and bigger mirrors, wider and wider telescopes, is that the bigger your mirror is, the more resolution, the more clarity of image you get. And to me, it's kind of amazing that these telescopes are able to get this type of clarity from the ground, because we're actually looking through the atmosphere. And the atmosphere itself should be moving around and blurring the image enough that we couldn't even see this. And this is actually something that I've had a lot of work doing in my lifetime. It's actually down to something called adaptive optics, and we've gotten very, very good at this in the last, I would say, decade. All of those little wires that you saw on the back of the mirror are all attached to little actuators that can push up on the mirror mechanically, little things that can push and pull the mirror, but in some cases only by a couple of atoms, very, very accurately. And they're able to push and pull this mirror. They're able to adjust hundreds of times a second. That's amazing. So you have all of these little mechanical actuators that are tiny, giving tiny little pushes and pulls. And what they're able to do is that if you can find out exactly how the atmosphere is distorting your light, you could actually take that effect out by distorting the mirror exactly opposite the way the atmosphere is moving. And what they do is that they have a big laser, and they shoot the laser up into the atmosphere, where it bounces off something called the sodium layer. And this is me geeking out a little bit, but I think it's worth it. I think it's a really fun story. You may not know that there's a sodium layer in our atmosphere that's actually the result of lots and lots of meteorites breaking up. So, meteorites come in, they break up, they form sort of a cloudy layer towards the upper part of our atmosphere. And there's specifically sodium atoms we can bounce lasers off of. So we can look through most of the atmosphere, bounce a laser off pulverized meteorites that are always up there. And then the laser comes back. And the laser path is all distorted by how the atmosphere, the air is moving around. But so you take your laser and you observe how the laser is shifting around, moving through the distorting atmosphere. And you take your mirror and you distort the mirror exactly to get that out, to take that out of your system. It's called adaptive optics, active adaptive optics. And that basically takes the atmosphere away. That's one of the reasons NASA has no more plans to build big optical telescopes in space. We can basically cancel out the atmosphere from the ground. And the only reason to go into space now is to go to wavelengths of light that don't get through our atmosphere. So there's your little fun with astronomy. Okay. All right. Now, back to the sun. So the sun, as we said before, is very hot. The atmosphere, the surface is approximately 10,000 degrees Fahrenheit. And that is hot enough to actually take hydrogen atoms, and it's so hot, the atoms have so much energy that the electrons get stripped right off. The electrons just take off. And so you're left with what are called ions, charged particles. The helium of the nucleus of a helium atom, or the nucleus of a hydrogen atom, they are positively charged, 1 or 2 protons, and the electrons are kind of free, not really associated to any atom. And so you're left with electrically charged particles. And remember, there's all this convection going on. So there's all this big gas, giant Texas-sized blobs coming up and down, and everything is so hot, it's electrically charged. What happens when you get lots of moving electric charges? You generate a magnetic field. And so much of the sun and its behavior has to do with magnetic fields. Magnetic fields can actually direct this electrically charged gas. The term for it is plasma. A gas that's gotten so hot, it becomes electrically charged. Simple. Some of the electrons just take off. So a lot of you are familiar with a bar magnet, which has, a north and a south pole, and the sun does too. The sun has a fairly clearly defined north pole and south pole. The problem is the sun is not a solid body. So things are going to start getting messy. And the thing that really messes up the sun's magnetic field is that the sun actually does rotate, like the Earth rotates once every 24 hours. The sun rotates approximately once every 29 days, but different parts of the sun don't all rotate at the same rate. The equator, because again, we're not talking a solid thing, we're talking a big ball of gas. The equator actually rotates a little faster than the poles do. And so you start off over here on the left with a nice magnetic field, north and south pole, but then all of a sudden the gas that's creating this electricity and this magnetism starts twisting as the equator of the sun starts moving faster than the poles. And before you know it, you've got a very, very twisted, messy magnetic field. And this is a real model from Goddard, from some of our heliophysicists, of what the sun's magnetic field was doing on a particular day. You see all of those green lines were from a computer-based model of observations based on data from what we were taking from our satellites. The magnetic field gets very, very messy. And as we said, the hot gas follows a magnetic field. And so that's why you see all these loops and these prominences and all these weird shapes of gas coming off the sun, is that all this electrically charged gas is following the magnetic field, but the magnetic field is really chaotic and complex. So there's all kinds of wonderful, this is a real picture. This is from the Solar Dynamics Observatory. The Solar Dynamics Observatory looks at the sun in extreme ultraviolet and X-ray light. So it's not a visible light picture. In fact, the surface of the sun is the darker part. And then right above the surface of the sun, you see these hot, bright areas where there is electrically charged gas trying to follow this complex magnetic field. And when these things get too active, some of the gas just breaks away. You get things like, coronal mass ejection, solar flares, stuff getting thrown out. And we're going to take a good look at that. So, of course, one of the things you get are sunspots. Those are probably the easiest ones to see with a solar filter. This is an area where the sun surface is just a little bit cooler. By no means are they dark. If you were up against a sunspot, it would be extremely bright, but they're a little cooler and therefore a little bit dimmer than the rest of the surface of the sun. And so when you're using a filter that takes out pretty much all the light and you can only see the brighter areas of the sun, they look darker in comparison. And once again, they're big. And what we're actually looking at there is a magnetic effect. So sunspots tend to come in pairs. And you're looking at basically the magnetic field doing a loop and having sort of a north and south pole and gas moving from one to the other. So the reason the sun, like I said, it's very simple, big ball of hydrogen burning away. But because of all that moving hot gas, it becomes a very, very fantastically complex thing magnetically. And this will start throwing material off. And so here, I'll show you. So one of the things they mentioned, what's making the sun's atmosphere so hot? It could be that there are lots and lots of tiny little flares we never observed before. And this is actually observations from a NASA mission. It starts with an image from the Solar Dynamics Observatory. And this is something that we've had up in space now for more than 10 years. It takes continuous high resolution images of the sun. And then it's going to go to another telescope, I think called IRIS, but let me play that. Oh, yeah, there we go. So we're going to take a look at a very detailed active region with some loops. And look at all those tiny little flares, the bright things at the bottom. Right on the surface of the sun, you see all these little jets coming up from the sun. We'd never seen those before. We'd never had the resolutions from the IRIS mission. And you can actually see all of these little things puffing up hot gas. And I think I might play that one more time. There we go. So yeah, I'll just let that. Another thing that we actually are observing when we see these loops, again, these magnetic field loops, is that there appears to be a gas like going the wrong way. There's all kinds of complexities to the way the gas is moving in these little systems. And all of that is probably actually sort of pumping out very, very hot material into the upper atmosphere of the sun. So that's probably one thing that's going on. And as the film mentioned, it's actually, it could be many things at once. We don't have to pick just one of these. This is actually going to be an image of the solar wind coming off the sun. So you have all of these things putting energy up above the sun, little jets putting hot particles up there. This is actually from a mission called STEREO. STEREO is a fairly old mission from NASA, and it features two spacecraft, as you might see, you might guess from the name, and it can see the sun from different angles from these two spacecraft. Now, what you're seeing here is the center of the image is a blue disk. They have something called a coronagraph, which is a little disk they can put in front of the sun to block the sun out, because the sun would be so bright that it would just completely overwhelm the detector. All you'd see would be the brightness of the sun. And if you want to see what's going on around the sun, all the material around the sun, they block out the sun. The little white circle in the middle, that's the true size of the sun. So if you could see the sun, it would be that big. And then there's basically a little metal disc blocking out the sun. And we're going to take a look at material going around. So those bright areas, that's the solar wind coming out, particles streaming away from the sun's surface. And I'll tell you what that little PSP is in a second. But we actually observe the solar wind regularly. And as you can see, it's not symmetric. There are areas that have lots of particles blasting off the sun, areas that have streams of material, other areas that are pretty quiet. And but we monitor this all the time. And I'm going to talk to you about a mission. Just play that again. I'm going to talk to you about a mission called the Parker Solar Probe. And the Parker Solar Probe is a spacecraft we have now orbiting the sun. And there it goes. There's a little blip that shows you the path of the Parker Solar Probe. We're actually flying it through the areas that are generating the solar wind. So that's a really fascinating mission. Okay, now, why is the solar wind so patchy? Well, the corona itself has different densities. How much gas is there right above the sun in this upper atmosphere? And you're looking here at images of the sun, again, taken in extreme ultraviolet or X-ray light. So you're not, the surface of the sun is dark. and you're looking at the very hot gas right above the sun that's actually glowing in millions of degrees. You're actually seeing the corona and the active areas. And wherever you can see through to the surface of the sun, that's where the dark area is. And these dark areas are called coronal holes. They're areas in the atmosphere of the sun, the corona, where there isn't much stuff, there isn't much gas, and the solar wind streams out through these coronal holes. So these are just two different days on the sun, one in 2012 and one in 2016. And you can see areas where you're seeing that dark surface of the sun, dark in X-rays. The surface of the sun just isn't hot enough to generate X-rays, at least not many. And you're actually seeing where that solar wind would be coming from. But those streams that you saw in that last video, different streams of particles, they come out of things like coronal holes. Okay, now sometimes something kind of violent happens. And I mean, things seem sort of violent, but I want you to have a look at this. Now I'll show you why one of the reasons understanding the solar wind is quite important. This is the sun as it was July 23rd of 2012. And this is again from the Solar Dynamics Observatory. It's taking a picture of the sun in extreme ultraviolet light. And there's a very active region, very bright active region here. And where you see the bright colors, that means the gas is very hot, millions of degrees. So let me play that video. And you can see that this is a time lapse. These things go pretty slowly. But in this time lapse, that whole part of the sun is just kind of crackling with activity. And another thing I want you to pay attention to, let me just play that again, is this is the image from the spacecraft. And as you can see here, it looks nice and clean. There's a bright sun and a dark region. But watch what happens when some of this activity goes off. So, okay, activity goes off, and then there's all this active area. You see how everything there's all these particles flying around all of a sudden. The sun actually sent off a big blast of material. And by the time it got to our spacecraft, it was causing the spacecraft to register all these high energy particles. So we've got stuff up there that's actually, a good blast from the sun can really affect it. So, here's what happened in a larger context. We're going to go to another one of those stereo images where you can see what happened in a larger part of the away from the sun. So again, before I play this, this black disc is where we have that little metal disc blocking out the sun. This is a picture of the size of the sun from that from the Solar Dynamics Observatory, another telescope, and then we're going to look at what the solar wind was doing. Okay, so let's watch here. Here's that little active area. And then these are all the streams of wind coming off. Let's see what happens here. Okay, that's pretty active there. A nice big belch of solar wind. Oh, whoa. Okay, look what happened to the detector. That detector basically got fried. I mean, we were able to recover it, but we needed to sort of shut it all down and reboot it and everything like that. That was a very dramatic super event in what we call space weather. The sun threw off trillions of tons of material all at once. It's technically called a coronal mass ejection. It's an extremely dense wave of solar wind that comes at us. And I don't know if any of you have heard of something called the Carrington event. The Carrington event is something that happened in the mid-1800s, where it was actually observed. We actually have solar observatories even at that time. There was a tremendous active area on the sun, just like here. They saw the big bright active area. And then a couple days later, as this big burst of particles came to us, something very interesting happened on the Earth. Now we're protected from high energy radiation. Our atmosphere is very good at absorbing X-rays and gamma rays and high energy stuff. Lucky for us, it's very good at that. These things are not a danger biologically, but this dumped so much electrical current from all that moving hot gas into our own magnetic field, the Earth's own magnetic field itself, that there was this basically, I guess nowadays they would sort of call this, an electromagnetic blast. And in the late 1800s, they didn't have a lot of technology that was affected by it, but famously they had telegraphs. And to get a telegraph to work, you connect your telegraph wire to a battery, and then you start varying the energy and you can send a signal down the wire. That day around the Earth, you didn't need to connect your telegraph wires to anything. They just started working all by themselves. There was so much current being generated, they didn't need a battery to power them. And some of the telegraph wires caught fire. So you can think about what that would do to us today. It would cause massive blackouts. This event that I'm showing you here was stronger than the Carrington event. The reason you didn't hear about it on the news, or at least from all the blacked out televisions once we got the power back up, it went off on the side of the sun away from the Earth. This is all taken from our satellites farther out in the solar system. Luckily for us, that active region was facing the Earth and we took pictures of it, but it didn't do the big blast until it actually rotated around the sun and it went off in the opposite direction. And I am so glad it did, because if you look at the date, it's 2012, right? I got so many damn calls from people saying that the world is going to end because of the Mayan apocalypse. What's going on, NASA? I was like, nothing, everything's fine. If this would have hit the Earth, everything would have gone down. We lucked out on that one. Whew. Anyway, so understanding the solar wind is important. And as we mentioned, we now have a spacecraft for the first time actually around the sun. And it's orbiting closer than anything has ever come to the sun. Some of these animations are a little misleading. It's basically about 4 times the diameter of the sun away. So if you think about the sun being, a disk like this spacecraft gets about 4 sun diameters away. So it'd be like over here. That's pretty good. That's pretty close. But it's not like right up against it. So I'm going to play a little introductory video. And this is kind of a fun video, because one of the questions we get all the time is, why doesn't this mission melt? So here's a little short video about the Parker Solar Probe and why it doesn't melt. Nice music too.
NASA's Parker Solar Probe is a mission to explore the sun. How can it do that? Why won't the spacecraft melt? Excellent questions. You can't face off with the sun without packing the right gear. This is why Solar Probe is equipped with a white shield that reflects heat off the front and keeps things cool in the back.
The heat shield is made out of a couple of different materials. One is carbon-carbon, which is a lot like the graphite epoxy you might see in your golf clubs or your tennis racket, but it's just been superheated. The inside is a carbon foam, which is just another form of carbon and is actually about 97% earth. It's a very lightweight way of making a very strong structure.
Nobody likes a needy explorer. Solar Probe can take care of itself, thank you very much. And that's because it has autonomy software that will keep its instruments safe and cool behind the heat shield.
We're too far away to joystick it into place, so it basically has to always be sensing whether or not the heat shield is in the right position and correct itself if it isn't. There are these things called solar limb sensors that are just poking out at the very edge of the shadow. And if those get illuminated, the spacecraft knows, oh, I'm going the wrong direction, and can actually right itself.
It's important to stay hydrated in the sun, even for a spacecraft. Solar Probe circulates water to keep the solar cells from overheating. It stays cool and keeps power.
So basically, water flows behind the solar rays and into the radiators. And so the water warms up when it's behind the solar cells and then cools down up at the radiators. And so that heat transfer is happening a lot like the veins in your body.
Yes, you read right. Heat is not the same as temperature. Temperature is a measurement, but heat is energy transfer. This matters because Solar Probe will be visiting the sun's outer layer, the corona. Like all stars, the sun is made of plasma. How tightly packed that plasma is depends on the layer. While the sun's corona has a very high temperature, the plasma particles are fairly spread out. So even though the temperature in the corona is 2 to 3 million degrees Fahrenheit, the heat around the spacecraft is manageable.
The corona and where we're going is actually not that dense at all. There are only a couple particles. And so when we think about it, those are very hot, but we're not touching a lot of them. It's the kind of like when you put your hand into an oven, and the oven might be at 400 or 500 degrees Fahrenheit, but your hand isn't at 400 or 500 degrees Fahrenheit.
Thanks to its design and destination, this cool, confident spacecraft is all set to explore. We can just sit back and chill as Parker's Solar Probe takes the heat.
This was a fun one because I actually got a chance to see this being tested and built at Goddard. So I love that. Okay, so Solar Probe launched a couple of years ago. I was at the launch. I was actually seated next to Eugene Parker, the person it's named after. That was the first time we've ever made a mission that wasn't named after somebody posthumously. But there was nobody else we could think of. He's 96 years old, I guess he was 94 at the time, and he's still alive. And he was the person that basically figured out there was a solar wind. And so, I mean, there was the best person to name it after. There have been lots of science results. You can actually go to the NASA website and learn about them. But one of the really interesting ones, this is an animation of that really just came out a couple of weeks ago, is that the solar wind very close to the sun appears to kind of zigzag. It's a strange idea that instead of the magnetic field just kind of going out nice and evenly, there are all these sort of whip-like structures where the field lines actually kind of do this. They sort of go back and forth very quickly. And they seem to have the effect of whipping the particles out. I was actually reading papers on this a couple of weeks ago. I was doing a little presentation. They don't know yet exactly why this happens. There are a couple different competing groups as coming up with explanations. This was just an observational fact that we saw the solar wind and the magnetic field doing these sort of whips, and we'd never seen anything like that before. It might have something to do with something called recombination, which it can be a little complicated, but it's actually not that bad. When you get magnetic field lines and they get very compressed, they're very close together, the magnetic field lines can actually sort of connect to the wrong field lines. They sort of get confused, and that can create this energy, this sort of explosive energy. For those of you that ever have to explain to the members of the public, black hole jets, right? There seems to be jets coming from inside the black hole, but nothing comes from inside a black hole. That matter, of course, didn't go into the event horizon. The area around the black hole had a strong magnetic field. And as material moved close to the black hole, the magnetic field got compressed and compressed and compressed until, boom, it actually sort of exploded along the poles because the magnetic field lines got confused and connected in a different way. It's really that simple. Just trying to do the math of that. I mean, Lord, I go to heliophysics seminars, like on PowerPoint slides, they've got triple integrals. It's like, I'm not going to figure that out on a PowerPoint slide. Anyway, so this wind of particles, now we're going to start talking about the effects of this, because now you understand what it is, fills up our solar system, and to some degree kind of defines the boundaries of our solar system. So this is this is an illustration, obviously, of the sort of bubble inside. Let me do this, yeah. So there's there's sort of this bubble that's being blown around us by this solar wind. The solar wind and this hot gas is kind of blowing a bubble around our solar system, and we live inside that, always being affected by the solar wind. The sun is also moving through interstellar space. The sun, I mean, it's not that it's moving this fast relative to the local gas, but the sun moves around the center of the galaxy at 500,000 miles an hour. It's going pretty fast. And yeah, I mean, the local gas is kind of moving with us, but we're actually moving through that local gas as well. And that creates sort of a shock wave in the direction that we're moving towards, we're moving around the galaxy, and sort of a tail drawn out. And this is what we call the heliosphere, basically the part of interstellar space that's influenced by the solar wind. And these little bright things are actually meant to show you that we think that this shock structure may even provide some protection for our solar system. The galaxy has very, very high energy particles called cosmic rays. We don't completely understand how they're generated. They may come from exploding stars, but they are stupidly high energy. I mean, you can get a single proton that's moving so fast, so close to the speed of light. It has the equivalent kinetic energy of a 100-mile-an-hour fastball. Really, that's scary. A single proton, and these things do hit the upper atmosphere sometimes, and we observe the shower of particles that come from them. But we actually think that this gas around our solar system may protect us from some of that. And you probably heard as well that the Voyager spacecrafts are now right outside this boundary. This is a nice schematic. It shows you, again, sort of the bubble that the solar wind blows around our solar system. And then this big sort of, big sort of bow shock, right? Like a boat going through the water. Here's the front of the boat, you're going through the water this way, and then sort of a tail behind you. And then Voyager 1 and Voyager 2 are kind of in this sort of outer structure of shocks as we go into interstellar space itself, the area where the space is not affected by the solar wind. Now, the solar wind also does one very important thing. It actually takes, the sun's magnetic field, the charged particles, can move out through the solar system also with that charged particles, with the solar wind. The solar wind, in effect, carries the sun's magnetic field around. And that helps protect us from some of these very high energy charged particles. Okay, now, we are not all that susceptible to the solar wind. This is one of our animations of this giant burp of solar wind called a coronal mass ejection hitting the Earth. And as you can see, as one of these blasts comes from the sun, pretty much everything moves around our planet. Something appears to be magically shielding our planet from the effects of this solar wind. And this happens way up above our atmosphere. So it's not even the fact that our atmosphere protects us. And here you go, there's the dynamic, there's the little schematic there. It has to do with our magnetic field. The Earth is extremely fortunate that we have an active metal core, a molten metal core moving around, generating a magnetic field. That magnetic field, remember we said magnetic fields can direct plasma, charged gas. In this case, they get directed around the Earth. They hit our magnetic field and they just bounce off and keep going. And things like the auroras, those are bits of particles that do get through. Actually, I won't go into where they're generated, but they get through and they come down close to the poles of our magnetic field. But lucky for us, we have this very strong magnetic field. And now as we go farther out into the solar system, we're going to talk about what happens when that's not true. Because this is really where the sun and the effects of the sun determine how a planet changes over time and whether it's habitable. And one of the more famous examples of this is our closest neighbor, Mars. Mars is a fascinating planet, and there for a long time now, for decades, but especially since we sent things like the Curiosity spacecraft, we have evidence that the entire planet was once very different, very wet, with rain and lakes and quite possibly a very large northern ocean, enough air pressure for water to exist on the surface. These days, the air on Mars is so thin that water would boil off almost immediately. We actually believe that this sort of change of Mars over time is directly due to the solar wind. And also the fact that Mars is red. This is something that a lot of people don't understand, because Mars is red because its entire surface was oxidized, combined with oxygen. So people say, wow, Mars must have had a lot of oxygen. Does that mean there was life there? Unfortunately, it's kind of the opposite. The oxidation is almost a signal of how life was lost there. What happened is that Mars doesn't have the gravity that Earth does. It only has, on the surface gravity, it's a little more than a half. And so, particles in its atmosphere can get a little bit farther up because there's not as much gravity. And because there isn't a magnetic field, Mars has no active magnetic field. We think it did once. Now there are little pockets of magnetic fields, but there's no big global magnetic field. All of that gas that gets farther up in the atmosphere is not protected by a magnetic field. The solar particles slam right into it. They don't go around. And what happens to a water molecule is that if a water molecule is up there, okay, so a high energy particle from the sun slams into it and it rips the hydrogens away from the oxygen. The hydrogens are light. They just stream off now. Off they go into the solar wind. The oxygen is heavier and it sinks and eventually combines with the rocks. The global red color, the oxidation of Mars, happened when the solar wind destroyed water molecules, ripped them apart in the upper atmosphere. The oxygen sank back down, the hydrogen just kept on going. And so today we have this amazing place. This is actually from the Curiosity rover. This is an alluvial fan, a river delta. Now dry, totally dry, probably been dry for more than 1 billion years. And we now know what happened to Mars's atmosphere and what happened to the vast majority of the water. It still has some water underground, it has ice caps and all of that, but the water was lost to space because of the solar wind and the lack of Mars's magnetic field. And so now we have a very dry, cold desert, and the air is very thin. Mars does have enough air to have some clouds. I think I've got a picture of that in a second. But we have hugely conclusive evidence that Mars would have been Earth-like at one time, meaning liquid water on the surface, thick atmosphere, moderate temperatures. But in the case of Mars, it didn't have a magnetic field. And the magnetic field just stripped everything away. The solar wind and not having it. Yeah, this is a picture. This is actually a picture from Hubble. This is real. It's a picture from Hubble of Mars, and you can actually see clouds. The clouds are actually clustered up by some of the big volcanoes. The volcanoes are not erupting. They've been dead for a long time, but they will actually affect the formation of clouds around them. And so there is some atmosphere. The atmospheric pressure on the ground on Mars on average is about 1% what the Earth is. So hopefully that makes ingenuity even more exciting, because we got this little helicopter to work with basically no atmosphere. They tested it in Chamber A in Houston, the giant vacuum chamber. So basically we had to suck out all the air to test this little thing. So I was amazed it worked. It was so much fun. Okay, just so you know, oops, I'll just mute that. Mars is still losing atmosphere today. There is still some atmosphere on Mars and it's still getting lost. And this is an animation based on data from the MAVEN mission. This is a satellite that we have orbiting Mars right now. And it is measuring how ions, charged particles in the atmosphere, are flowing off of Mars's surface. And as you see here, the solar wind is smacking into Mars without much to protect it. And the way it's working is that there are actually these plumes of ions that are coming off the sun-facing side of Mars. And this is something that we're observing now. We have now for several years with MAVEN. As it turns around, you'll see it actually compared to some real MAVEN data. The computer animation, which looks a lot nicer versus the actual measurements. But the computer animation was based on those measurements. Mars is losing about 9 tons of atmosphere a day. So even with as little atmosphere as it has, it's still losing 9 tons a day. Oh, and there's MAVEN. Hey, great. Yeah. Okay. Let's see, what's this one? Yeah. All right. Now, there's another planet that has, is also a really interesting example of what happens when you don't have a magnetic field, and that's Venus. Venus, we have no idea. It's very much like the Earth mass-wise. It's hot. It's a little closer to the sun. It didn't cool down. So why doesn't it have a magnetic field? It's a big mystery. Hopefully, we're going to go back to Venus sometime soon and find out more about the planet. But Venus is an example of what happens when you have lots of atmosphere, but you're not protected from the solar wind. So in the case of Mars, it just stripped it all away. Mars didn't have enough gravity to really keep it down. Venus does. Venus has a good amount of gravity. It's very similar to the Earth. But the same process happened with the water leaking away. And with the water vapor, coming up to the top of the atmosphere, no magnetic field to protect it, it split the water off, and heavier stuff. In the case of Venus, it was mainly carbon dioxide, but also heavier things like sulfur. And so what happened to Venus over billions of years is it lost the water cycle. There was no way to, basically it got so hot that carbon was baked out of the rocks, carbon dioxide, that just got thicker and thicker. Any chance of water raining down, combining with the carbon dioxide was taken away by the water. And so you end up with this kind of very thick atmosphere with a witch's brew of elements. The clouds are made of sulfuric acid. And, as you know, that the temperature is so, the carbon dioxide, the greenhouse effect is so great on Venus that the surface temperature is about 800 degrees Fahrenheit. And with atmospheric pressures that would crush you. And in fact, we've only landed successfully, all but the former Soviet Union landed on Venus several times. You were basically able to take one picture before the spacecraft fried. And these are real pictures, real color pictures from the surface of Venus. The yellow color is from the sulfuric acid clouds. And it does rain, but the surface is so hot that the droplets never reach the ground. It vaporizes well before it ever hits the ground. But a very unfriendly place due to the lack of water. And there's another thing that we think the lack of water does. We really take water for granted. Water combines geologically with rocks, metamorphic rocks. Lava can get combined with water deep under the surface of the Earth. And it turns out that plate tectonics and the way a planet works, the way a planet can basically shed energy by plates moving around and there being volcanoes to kind of let off steam. Plate tectonics may have a lot to do with the water content inside rocks. We're not talking about like water droplets actually sort of lubricating. We're talking about the rock structure itself. You may not know it, but granite is a very water-rich rock. If you have sort of a cube of granite like this size, there's about the equivalent amount of water in that. There's water actually in the molecular structure of the minerals. And that provides an elasticity for the rock itself to sort of be more crushable and movable and form lava more easily. The rocks on Venus got baked. All of the water was released and then the water lost at the top of the atmosphere. And because of that, Venus does not have anything like plate tectonics that we do. Instead, and this is one of the big mysteries of Venus, we see the entire surface is about the same age. There aren't some areas like the moon that are heavily cratered and others that are new. And there are lava flows that seem to go almost all the way across the planet. I mean, this bright area is an area, this was taken by a radar image, a radar going through the clouds. This bright area is a lava flow that may actually go for thousands and thousands of miles. And there's some evidence that the entire planet of Venus, instead of having plate tectonics the way we do, energy builds up and builds up and builds up, but it doesn't have any plates to release the energy. And so every like 500,000 years or so, the whole thing just goes super volcano, the whole thing. Basically, the whole surface goes lava. We don't know that's true, but that's one of the ideas about how Venus could possibly look like this. And we still do not understand why Venus has no magnetic field. That's a mystery. Going a little farther out, we're almost to the extent now, even Pluto, right? I mean, to the very, very end of our solar system, okay? Pluto, you wouldn't think is very much affected by the solar wind. But when we got out there, we found out that Pluto does have an atmosphere. And the atmosphere, this is controversial. It may be kind of sporadic. Pluto's closest approach to the sun was sometime in the 1980s, and now it's going back out farther away. It's in a fairly elliptical orbit around the sun. And so its temperature changes quite a bit. When it's nearer the sun, it heats up, and when it's farther away, it cools off. And one of the reasons we sent New Horizons out now is or a couple of years ago, is we wanted to catch that warmer phase of Pluto. Maybe there'd be more active ice. We didn't know what we would find. And sure enough, here's Pluto from the New Horizons spacecraft. There was a wonderful, giant, I mean, million square mile glacier of nitrogen ice that you see right here that we call a Sputnik Planum. And it's an amazing thing. I mean, these high resolution photographs are just incredible. You can see almost like we're talking about the sun, there's actually convection going on in that ice. There's all these little surfaces of bits of the ice that are getting warmer and moving upwards and then cooling and going downward. We actually think that underneath that very well may be a reservoir of liquid water. That's pretty cool. Liquid water on Pluto. Nobody expected that. And Pluto does as well have an atmosphere. This is a real picture from New Horizons. And you can see those tenuous bands up above the surface. These are different density bands in the atmosphere. The atmosphere is mainly nitrogen and methane. And this picture really gets me. This is at the edge of that glacier. Let me go back one, you can sort of see. So if you notice, there's sort of these mountains over here, and you're looking down on mountain peaks, and then there's this glacier kind of up against the mountains. And these mountains here are about 8,000 feet high, and they're glinting in the dim sunlight. They're actually made of pure water ice. Ice at that temperature, only about 40 degrees above absolute zero, is so strong, you can actually build mountains out of it. Just beautiful. All right, so can the sun affect things other than planets? And does that affect the habitability of worlds too? Well, another thing that we are now studying the effect of is the sun on asteroids. And this is actually an animation that's a little bit frightening. These are all the near-Earth asteroids that actually cross the Earth's orbit that have been detected in the last couple of years. As we've gotten better at observing these small bodies, mostly through infrared surveys, infrared light, where you can see things that are warm, we actually at NASA now have telescopes dedicated to finding these near-Earth asteroids. And one of the reasons you haven't heard about any upcoming collisions, or we don't know of any, we've mapped out the paths of all of these that you've seen. We think we found pretty much everything that's about half a mile or larger, like 95% of that. There's always a chance we've missed something. And the question is, do we really know that they're in orbits where we're safe? So I'm going to show you this. We've mapped out all of the orbits of these asteroids that cross the Earth's orbit. We know exactly where they are. We know the orbital dynamics. But there's actually a complicating factor, and that's how they interact with the sun. And so this is a short video, again, very short, on something called the YARKOVSKY effect. It could be that sunlight itself changes the orbits of these asteroids, and we don't really know by how much yet. This is one of the things where we say that we don't know of any dangerous encounters for the next couple hundred years at least, but how well do we actually know the orbits, and how do we know how they're changing? So let me play this for you. Oh, let me give you some sound.
From a distance, everything in our solar system appears to be in its place. However, if you take a closer look, sometimes you can find asteroids, like BENNU, leaving their home in the inner asteroid belt and passing very close to Earth. Most other asteroids tend to stay grouped together in a few regions of our solar system, yet some still end up in our backyard. So once these asteroids get close, what makes the difference between a near miss and a potential hit? NASA's OSIRIS-REx mission will help better answer this question when it visits BENNU, but scientists think that a force called the YARKOVSKY effect might be an important part of the answer. So how does this effect work? Well, like Earth, most asteroids rotate slowly as they move through space. During the day, the surface of the asteroid is illuminated by the sun, so it absorbs heat and grows warmer. During the night, however, the surface cools down, emitting the heat it absorbed as radiation. This radiation exerts a force on the asteroid, acting as a sort of mini-thruster that can slowly change the asteroid's direction over time. On larger asteroids, this doesn't amount to much, but on small ones, it can make a pretty large change over time. Because the surface emits the most heat radiation at the end of the day, the direction the asteroid rotates can ultimately determine what happens in the long run. Other factors, such as composition, asteroid shape, and surface features, can modify the magnitude and direction of the Yarkovsky thrust. By studying the Yarkovsky effect on BENNU with the OSIRIS-REx spacecraft, NASA scientists hope to better predict how an asteroid might move through the solar system and whether it poses any danger to us here on Earth. So the next time an asteroid starts gradually moving into our neighborhood, we'll have a better idea of exactly where it'll end up.
So it could be that we really don't know the paths of these things yet. And, you know, that's something where, OSIRIS-REx. So it could be that we don't actually know where these things will end up because we don't really understand how asteroids absorb heat when they're facing the sun and how they emit it when that side moves around to the dark side and cools off, the cooling off itself creating a little bit of a thrust on the asteroid. One of the things that determines that is how dark is the asteroid, how fine is the soil. I mean, soil kind of implies it was alive like on Earth. They call regolith, you know, the sort of sandy stuff. And the last thing I'll show you is I just want to play a little bit of this video. You can watch the whole thing at NASA. When we actually got to BENNU, this asteroid, when the OSIRIS-REx mission is going to be learning all of this, it turned out to look a lot different than we thought. So I'll just play a little bit of this.
As we started to approach BENNU from a distance and it started to fill up the camera field of view, it looked exactly like we thought it would, with a few boulders sticking out. But as we got closer, we expected to see a very sandy surface with maybe a few boulders here and there. And what we saw is very little sand. And we saw these mountains, we saw boulders, we saw rocks, and we saw very few areas that had the sandy surface that we were expecting and what we had designed to.
We have never done this before. We're actually going to collect a sample and bring it back down to Earth for further examination by scientists.
In order to achieve that objective, the OSIRIS-REx spacecraft has been navigating around BENNU for about the last 2 years, studying it in great detail, and also overcoming a number of challenges that BENNU has presented. We were looking for locations on BENNU that were 50 meters in diameter, relatively flat, and covered with fine-grained material. And by fine-grained material, I mean stuff that's the size of a dime or smaller. We realized that there were no sites on BENNU that even came close to meeting this criteria. Everywhere we looked was too small and covered with boulders. So we actually had to fly a number of additional closed passes over the...
I will end it there. So I think a lot of you know what happened with the OSIRIS-REx mission. It was a huge success. I'd be happy to come back another time and talk all about just that mission, but I better wrap it up. I know we're close to 4 o'clock. So, you know, the theme of solar power, you know, it's something you can interpret a lot of ways. And I think that a lot of people don't realize how much the sun is responsible for the evolution of worlds, the evolution of our planets. Venus, Earth, and Mars all started out, we think, fairly similar. We think Venus, by the way, too, probably had global oceans, a water cycle, you know, something very, very much more Earth-like. But all 3 of our planets diverged because of how we interact with the solar wind. And it's actually one of the big challenges in trying to figure out whether planets around other stars that we can only see as measurements. I mean, we've never been able to take actual pictures of them yet. How do you know if they're habitable or not? They could be the right distance away from their star. They could have about the right mass like to be Earth-like, but do they have magnetic fields? Has their star stripped them of, you know, any sort of water? That's something we can't measure at all yet. They're too far away. You know, a big deal with whether a planet is habitable and whether it stays habitable over billions of years is how we interact with our star, and in this case, the solar wind. And with that, I will wrap it up and take some questions.
Okay, well, thank you so much. That was really fascinating.
I'm sorry I had more. I went a little bit long. I apologize for that.
And I know that you have to wrap up. We do have one question, but maybe other people can, if they have questions, they can put them in the chat. How do they keep the DKI telescope optics cool? Jim thinks it must get quite hot.
Oh, because of the solar imaging, yeah. It's funny. I don't know that offhand, but I bet you can go to their website. I mean, I don't know whether they use. I mean, every time I've done observations, I've used lots of liquid nitrogen. I mean, there's always, that keeps the detectors cool. But as far as the optics, I don't know, because you're talking about that giant mirror, right? So you can research the coating on it. You can see how it works. That's one I haven't been to yet. So I don't know. I encourage you to research it. Okay, well, I guess with that, I'd better head off. But like I said, I would be happy to come back and talk about, the topic of your choice. And really nice to be with you all today.
Okay, well, thank you so much, Michelle. I wanted to tell everyone else that we are going to have a series of programs. We were driven by solar power in the context also of climate change. So there'll be more talks about the sun and also about climate change. We have a quick question. I had a hard time interpreting the SDO coronagraph images in 3D. Can you help? Asks Andy.
I'll see. I'm trying to think about how you could do this. So you can think about the sun, it's sort of, the STO spacecraft is orbiting the Earth, and it's so far away that it could actually just put, that little metal, it can basically just put a little metal ball, a little metal disc in front of the sun. And then it blocks out the sun's light. STO and stereo, both of those, they orbit fairly close to the Earth. Stereo actually goes out around the sun. Sorry, too complicated. Basically with the coronagraphs, you just think about the telescope actually having a little metal plate that it can steer itself and put right over where the sun is in its imager. And then it can just take out that glare so it can see all of the other stuff going around. You're going around off the sun. I bet Jim could do a pretty good job explaining that too. So that's kind of a hand waving. It's like they think of it like this, but anyway, yeah.
Okay, Michelle. Well, thank you very much, and we'll be in touch for more.
Sounds
Thanks
good.
so much.
Bye.
Bye-bye. Thank you.
Thank you.
Thanks everyone for joining us.